Okay, this is the video for thermal physics, and this is for the AQA A-level spec, normally what we study at the start of year 13. And we're going to look at today heat, internal energy and temperature, explain the difference, and we're going to look at things, how do we describe something that's hot, what do we mean by that, and consider the amount of energy required in order to heat particular substances. Okay, so first off, some definitions. Internal energy of something, this is the energy contained in the molecules of a material due to their position and movement. Internal energy can be stored. So if you consider the bath is a store of internal energy. Okay. Now heat, the actual definition of heat is the flow or transfer of energy through a material. So by definition, you cannot store heat. For you to store heat, you have to heat something up. So transfer the heat into it, and then you can store the internal energy that's been transferred from the heat. Okay, now temperature is only really a measure of the average kinetic energy of the molecules in a system or an object at a particular location. So if you were taking the temperature of that bath, then you would put a thermometer in or a temperature probe in, and you're only really getting an idea of the temperature at a particular point. And what you're doing is averaging out the kinetic energy of all the molecules or atoms at that point. Okay, so try and keep those in your head as we go through this for today. So transferring heat, internal energy changes going on between the spoon and the tea. Well, this is fairly straightforward. The internal energy of the spoon increases and the energy of the tea decreases. So we are saying that the tea heats the spoon. Okay, there's a transfer of internal energy via heat from the tea into the spoon. If the tea is hot and you put the spoon in when it's cooler at room temperature, the tea would in effect heat the spoon. And this is some very sort of early lower school revision. If one object is hotter than the other, heat transfer takes place by either conduction, through solids, convection, through fluids, liquids or gases, or radiation, which is part of the electromagnetic spectrum. So just make sure you've got an idea of the methods of heat transfer. And heat is transferred due to the temperature difference. Remember, if there wasn't a temperature difference, there would be no heat transfer. Another example, this is where you've got the brakes on a car. Now that they start off at the same temperature, so the brake pad and the discs, here you can see it glowing, started off at the same temperature. So what's going on? Where's the heat come from? Well, here we've got the idea of work being done. So work is being done by the frictional force between the brake disc and the brake pads, and the work is done in order to stop the car or to transfer the kinetic energy. So the temperature of the brakes increase as they gain internal energy from the kinetic energy of the car, and again the transfer is done by heat. In terms of a light bulb, what's going on here? Why does a light bulb get hot? Well, again, work is done by the circuit, and work is done effectively by the electrons are being pushed through the circuit, and they're being pushed through against the resistance. So the internal energy of the filament increases, it gets hotter. As the electrons are forced through, work is done on the filament, so therefore the energy of the filament increases, which we get out as heat. It gets hotter. Okay, so why do these two examples not keep getting hotter and hotter and hotter and hotter? So here we have the idea of energy flow into and out of an object. So internal energy in an object changes as a result of heat transfer in or out of it, or work being done on or by the object. So you'll have a constant temperature or a constant internal energy if there's no heat transfer or work done. Heat transfer and work done balance each other out. So the energy lost equals the energy gained. And if this is the case, you're in a situation which is what is known as thermal equilibrium. Okay, so nothing's going to get hotter and hotter and hotter. Okay, these are the classic pictures you've probably seen since like way back in year 7. Solids, liquids and gases. What do you need to know? You've just got to remember all the basic stuff you were told a long time ago. Strong bonds between molecules vibrating around a fixed point. Energy transferred to a solid increases the kinetic energy of these molecules. At the melting point, the molecules gain enough energy to break bonds and move freely. When they do that, they transform into a liquid. So after the solid melts, it melts into a liquid. Now there's random movements between molecules, but they do remain in contact. They will fill a container at the bottom of a container effectively. The energy transferred to liquid increases the kinetic energy of the molecules even more. So the more you heat this, the faster these move around, the more kinetic energy they have. And at boiling point, some molecules gain enough energy to escape. When they do that, they escape escape into a gas, they boil or evaporate, and the random movement between the molecules that are now, they're much further away. So the spacing between them, between a solid and a liquid, is kind of pretty much the same, but this is to do with the movement between a solid and a liquid, but between a liquid and a gas, the spacing is radically different. Okay, they've had a lot more kinetic energy transferred to them, so they've got a lot more energy to move around faster. The collisions with the container are responsible for the idea of pressure, which we will come on to later in this topic. Okay, so let's quick look at temperature and temperature scales. These two people are the two main sort of people in the story. The Celsius scale, this is Celsius. It's defined by fixed points. It's what we tend to use. Most people talk in degrees Celsius. It's defined by the ice point, the temperature of pure melting ice, and the steam point, the temperature of steam at a standard atmospheric pressure. But really, in science, we more often use the Kelvin scale. This is a Kelvin. It's defined by something called absolute zero, which is the lowest possible temperature. And you might think, well, how do we get the lowest possible temperature? Surely you can always go colder. Well, in terms of our ideas of particles, if you cool and cool a gas down, it ends up the molecules will move less and less and less until the point where they stop moving. And when they stop moving, the effective volume, if the volume has been reducing and reducing and reducing, when they stop moving, the volume will approach zero. So you can do experiments and measure how the volume of a gas changes with temperature, and these are these red data points here. So this is the volume of a gas at particular temperatures, and then you extrapolate the line all the way back until it crosses the temperature scale at zero volume, and this would be the absolute zero temperature, and it's got the minimal or the least internal energy, so its temperature cannot be reduced anymore. And this, when you do the experiment, and you might have done this in the lab, or we'll do it later on in the videos, the absolute temperature is minus 273.15. So the temperature in degrees Celsius for 0 degrees Kelvin is minus 273.15 degrees Celsius. Okay, so just then at the end of this specific heat capacity, what does the temperature rise of an object depend on? Okay, so the change in temperature will probably depend on the amount of mass of an object you've got. It's also going to depend on the amount of energy you supply, so how much energy you put in, which is delta Q, and it's also going to depend on the property of the material, which is known as the specific heat capacity. So this is a property of material. It's a constant for material, and it is how much energy it takes to raise 1 kilogram by 1 degree Celsius. Okay, so it's the amount of energy that it takes to raise 1 kilogram of material by 1 degree Celsius. So from that we get the specific heat capacity formula, which is delta Q, energy supplied, is equal to the mass times the specific heat capacity times the change in temperature, the delta T. Okay, and this is the definition, as I've just said, which it is worth your learning for the exam. The units, if you rearrange this to get C, it's C equals Q divided by MT. So this, remember, Q is energy, so this is joules per kilogram per Kelvin. Sometimes you get it quoted in Celsius, but normally you have to quote it in degrees Kelvin. Okay, then experiment you may have done. Calculate experimentally the C value, the specific heat capacity for aluminium and brass or copper. Set up a heater. Note the current and voltage. Note the rise in temperature every minute, and we're going to use this information to plot a graph. So here's our formula that Q equals MC delta T. I'm going to replace Q, the energy, with IVT, which is current, voltage, time elapsed. And the reason for that is if we come over here, we know that electrical work done is QV, which is charge times voltage. Don't get mixed up with the Q's, this is charge. We know that Q equals IT, so inserting this Q into here, we can get the work done is equal to the current times the time times the voltage. And this work done is the same as this energy transferred. So we've replaced the Q over here, the delta Q, with ITV. So our formula is ITV or IVT, I've just changed it, is equal to MC delta T. Let's just sort of rearrange it. So we'll have delta T is IVT divided by MC. And now this delta T, if you do an experiment, the change in temperature is going to be the temperature you get to, so this is the final temperature T, minus the temperature you started at. So this is T minus T room is equal to IV over MC multiplied by T. Okay, so if we just rearrange that to make it look like a straight line graph, we can say that T equals IV over MCT plus T room. I've just brought the T room over, and here you can see Y equals M X plus C. So if we plot on the y-axis T, the temperature, if we plot on the x-axis little t, the time elapsed, our gradient should be IV divided by MC, and our intercept should be the room temperature. Okay, so our gradient we should be able to say is the power, which is IV divided by MC. So in terms of a graph that you could get from doing this, this is my graph. I've just plotted it in Excel. So you can see my gradient is 0.0734 and my intercept is coming out as being plus 15. So that'll be the room temperature of about 15-16 degrees. So if we just handle the gradient, we know that the gradient from here, the gradient is IV over MC. Gradient is IV over MC. 0.0734 from the graph is equal to, when I did this experiment, I had a heater that we supplied a current of 3.12 amps at a voltage of 9.9. The mass we used was a kilogram of brass, so that's M is 1, and obviously we're trying to find C. So if I just rearrange this, I get a value of C of approximately 420 joules per kilogram per Kelvin, and if you look online, you can get the data for brass, which is about 380. I know brass, there are different varieties of brass, so it's very difficult to get an exact specific heat capacity. Okay, so hopefully you've seen what we mean by the definitions, what specific heat capacity is, and then an example of an experiment that could be done to find the specific heat capacity of a particular material.